All right, in this video, we're going to go through the curve sketching section of the calculus textbook. So that's section 4.5. The previous video was a review of everything we've learned so far in chapter 4 that pertains to curve sketching. And I wanted to do this review because I want to make sure that you absorb all of the concepts that pertain to curve sketching. This is really important. This section is really important. As far as your ability to apply calculus, or specifically, I guess, more differential calculus, calculus 1, if you understand curve sketching and all the topics associated with curve sketching, then that really shows that you have a deep intuitive understanding of differential calculus. So this is really important as far as like applied calculus. You might be saying, well, what does curve sketching have to do with, sketching a curve have to do with applied calculus? So yeah, like in your respective field, in biology, physics, business, engineering, you're not necessarily going to be sketching curves, but what you're going to see though, as we go through this section and as we work example problems on curve sketching, in order to sketch a curve, you have to have an intuitive understanding of all the different ways a function or an equation is behaving. And so when you think about that from the standpoint of not curve sketching, but just analyzing an equation, analyzing a function, forget curve sketching, just, okay, so all of these different steps that we're going to do here, that you do prior to sketching the curve, instead of sketching the curve, you could do any one of these as a way to analyze the function. Just from like a function that has to do with business. You might want to see the asymptotes. Like, so how does, as a variable goes to infinity, what does the overall function do? Think about that from just analyzing that from a theoretical standpoint. As the cost goes to infinity, what is the function doing? As the cost approaches a certain value, what is the function doing? There's another video there was a video that I posted in the limits part of the course where it was like an equation based on relativity or something, and we took the limit as, I forget what it was, maybe the velocity went to infinity, and the overall function approached the speed of light as that a variable went to infinity. And so that's, you can think about that from an intuitive standpoint. What does that mean from a physics standpoint? And so that kind of analysis you can apply to anything here that you do in regards to curve sketching. If a curve is concave up or concave down over an interval, well, okay, like if like an economics function, if it's concave up in some area, well, what does that mean that's happening from an economic standpoint? Maybe it's a certain time of the year. Maybe more people are coming into the city or something, things like that. So you really want to understand how to curve sketch, not in relation to sketching a curve, like an artist, but so that you have an intuitive understanding of how you can use calculus and algebra to analyze equations and functions. Okay, so it says, so far we have been concerned with some particular aspects of curve sketching: domain, range, and symmetry in chapter 1. So yeah, chapter 1 was pre-calculus, and this was, which is like algebra concepts relevant to calculus. And so we're going to mix in when it comes to what we're going to learn here in this section, we kind of bring calculus and algebra together to analyze a function. And so like you'll have a function and you'll first see what's its domain, what's its range, is there any symmetry? Those are algebra concepts. All right, then you can take limits, analyze continuity, look for asymptotes. That's what we did in chapter 2. And then derivatives and tangents in chapters 2 and 3. And then extreme values, intervals of increase and decrease, concavity, points of inflection. And that's what we've done so far in chapter 4. That's what I reviewed in the previous video. And then it says in L'Hopital's rule in this chapter, this is chapter 4, L'Hopital's rule, but I skipped L'Hopital's rule. I want to come straight to curve sketching. L'Hopital's rule is just it's a way, so if you're trying to evaluate a limit, you can use all the techniques that we learned in chapter 2, but you can also apply L'Hopital's rule, which uses differentiation to solve a limit. So that's another way you can solve a limit problem. But L'Hopital's rule, this section also talks about indeterminate forms of limits, which it is an interesting way of how you can analyze certain types of functions. And so, I guess it might have been nice to do this section before we got to curve sketching, but I want to just come straight to curve sketching. But we'll see that in the next video, we're going to go through L'Hopital's rule, and you're going to see how in certain situations you can analyze a function or an equation if it might have indeterminate forms. So, for example, if you have a function g of x over h of x, and you might say, well, when the denominator goes to 0, the x values that makes the denominator 0, those are vertical asymptotes, let's say. Well, not necessarily if when you approach a certain x value that also makes g of x go to 0. If as you approach an x value that makes both g of x and h of x go to 0, then you can't necessarily say that's a vertical asymptote. So that's like an indeterminate form. And there's different kinds of indeterminate forms. So that'll be interesting to look at in the next section. It is now time to pull all this information together to sketch graphs that reveal the important features of functions. So you see that this is what I'm talking about. This is why this section is so important, because we're pulling all kinds of information together from algebra and calculus to reveal important features of functions. So yes, again, your features that help you graph the function, but forget about artistically graphing the function. You can analyze these features. It's ways you can analyze and understand a function. All right, you might ask, why don't we just use a graphing calculator or computer to graph a curve? Why do we need to use calculus? So this is interesting. This question is interesting. It's saying, why don't we just use a graphing calculator or a computer to graph the curve? Why do we need to use calculus? And well, one reason is because you want to intuitively understand what you're doing. But there's also, they talk about there's some potential ways you can make errors if you just rely on, even if you intuitively understand what you're doing, there's ways that you can potentially make errors if you just rely on a graphing calculator or a computer. And that's what we're going to talk about in section 4.6. In the next video, we're going to go back to L'Hopital's rule, section 4.4. But in section 4.6, we'll talk about, using software or graphing calculators versus doing it by hand, and kind of the drawbacks and the things to look out for. So that's what these 3 paragraphs are talking about. All right. So guidelines for sketching a curve. The idea is, what they're saying here is, you start off with curve sketching, you have a function or just an equation that's not a function, maybe. Well, okay, they're just talking about functions, but I mentioned this in the previous video. We're with curve sketching, we're only going to analyze functions. It's not like you can't, if you had a relation like a circle, it's not like you can't apply this kind of analysis to a circle. It's just, it's different because, like, for any x, you'll have 2 different slopes potentially and 2 different concavities. And so you can still analyze it in the same way. It's just, for the sake of analysis and to keep it simple, we just look at functions to where there's only, for each x value, there's only 1 slope and things like that. Okay, so you're given a function. You just have a function, and you can kind of think about that. You don't necessarily know what it looks like. That's the idea. That's what, if you knew exactly what it looked like, then you wouldn't need, you could just sketch the curve. So you don't necessarily know what it looks like. You can think about it that way. So in order to sketch it, or equivalently, you can think about to analyze its behavior. What they're saying is that they list a bunch of different steps that you go through, and you just start off by just writing all this stuff out. And then once you have all this stuff written out, then you can analyze the function or sketch the function. So the first thing you'll do is determine what is the domain of the function. And this is important. In the previous video, I forgot to do this for one of the problems, and you saw that the issues that it caused. So, like, it was something like the function was like f of x is equal to x squared plus 1 over x minus natural log of x, something like that. And so the step 1 would be you write what the domain is. And so here you can't input an x that's less than or equal to 0, because the natural log of x that's outside the natural log of x's domain. So the domain here is x is greater than 0. Well, the first thing this does is it lets you know the interval that you're looking at. So we're going to be analyzing this function, its endpoints, you can think about it as every function has two endpoints. This has endpoints, it goes from 0 to infinity. Infinity you can think is like an endpoint. Okay, and so but if I didn't specify the domain, what happens is, one step that you do, we'll see it in a little bit, is you find the critical numbers. So you would say, okay, f prime of x is equal to 2x, and then minus 1 over x squared minus 1 over x. And so you set this equal to 0, and just the way it works out, you could potentially, because you've gotten rid of this natural log of x, you could potentially get an x value that's less than or equal to 0 as a critical number. In fact, you can already see a critical number is going to be x is equal to 0 because the first derivative doesn't exist. But even if when you set this equal to 0 and you solve for x, you might get negative x values. Okay, well, because I didn't specify the domain to start with, I assume that like -2, x is equal to -2 is a critical number. That's not a critical number. It's outside the domain. And x is equal to 0 is also not a critical number. Well, one, it's outside the domain because x has to be greater than 0, not equal to 0. But even if this domain did include equal to 0, you don't really look at an endpoint as a critical point, right? Because in this case, okay, 0 is part of the domain, but there's nothing to the left of 0 that's part of the domain. So you don't really look at that as a critical point. So you see that's the idea of why you want to specify the domain first. You specify the domain, you can see your endpoint. So, like we talked about in the beginning of this chapter, if you had something like this, you want to specify the domain. It goes from this x to this x. So now you see what your endpoints are. All right. So you're given the function. You write what its domain is. Then next you find the intercepts, the x and the y intercepts. This is still algebra, right? So how do you do that? You set x equal to 0, solve for y, that's the y intercepts. Then you set y is equal to 0, solve for x, that's the x intercepts, and you just list those out. We're not drawing the curve yet. We're just listing all this stuff out. All right, next you analyze the function to see if it has any symmetry. And so if you need a review on the concepts of symmetry, go to the algebra playlist. But remember, there's 3 forms of symmetry. You can be symmetric about the x-axis, the y-axis, or the origin. But since we're just dealing with functions, then there's only 2 forms of symmetry. There's only symmetric about the y-axis and about the origin. Because you can't, if you're symmetric about the x-axis, then you need 2 values of y for a certain x, right? Like here, you're symmetric about the x-axis, but that's not a function. So this is symmetric about the y-axis. That could be a function. The idea is you plug in minus x for x, simplify, and you get the same function back. So if you flip this about the y-axis, the graph doesn't change. And then there's also symmetric about the origin. So if you flip about the x-axis, you don't come to the original curve. So it's not symmetric about the x-axis. If you flip about the y-axis, you don't come to the original curve. But if you flip about the x and the y-axis, you come back to the curve. Okay, and that's called, so symmetric about the y-axis is called an even function. Symmetric about the origin is called an odd function. And you test for an odd function if f of minus x is equal to minus f of x. And that's the only 2 potential forms of symmetry when it comes to a function. Well, there actually is periodicity, but outside of being periodic, these are the 2 forms of symmetry when it comes to a function that you'll test for that. You'll plug in minus x for x and see if you get the same function back. You'll plug in minus x for x and see if you get minus f of x back. And then if you come here, you can also test for, there's a periodic symmetry, which is if you take, so the idea is like if you have sine of x plus some number is equal to sine of x, then this is periodic, has periodic symmetry with period 2 pi. So you can test to see if you have a periodic function. You see, here's the period. The period is p. It's not just trig functions. There's a lot of different functions like that could be periodic. So not any of the main ones. The main ones that we learn in algebra and trig. Unless I'm forgetting one, but in the main functions we learn in algebra and trig, the only ones that are periodic are trig functions. But there's other special types of functions like that can be periodic. So you can always test for periodicity. But when it comes to the trig functions, so like sine has a period of 2 pi, for example, but tangent has a period of pi. Tangent is periodic as well. Okay, next you analyze for asymptotes. So there's horizontal, vertical, and slant asymptotes. In this section, I would group in I would add a step, and I would group it into the asymptote section. You could start by analyzing the endpoint behavior. That's one thing they don't include in this section that I would include is analyze endpoint behavior. So what do I mean by that? Well, all right, you know the domain of the function. Let's say you have, it doesn't go off to plus or minus infinity. Well, it's something like this. Well, okay, you could, like this endpoint, you could analyze it, just plug in the function at this value because it's defined here. But like here, it's not defined. You can't plug in the function here, but you could take, if this is f of x, you could take the limit as x approaches this value from the right of f of x. You see? But more than that, you could take the limit as x approaches this value from the right of f prime of x or f double prime of x. You could do that same thing over here for f prime and f double prime. And that would help you with curve sketching. If you're trying to sketch it really accurately, you could take all kind of limits of the first and second derivative all over the place. And that could really help you if you're trying to do a really accurate curve sketch. You could take, if you know the slope of the curve coming into this point, that would help you to sketch that curve exactly with the right slope and even curvature. But again, more from an analysis standpoint, you could just see how the curve, like just analyzing the function just from a physics standpoint or whatever, how the curve is behaving as it approaches the endpoint. Now, if let's say the curve goes off to plus or minus infinity, or maybe it could have one side is like this and the other side goes off to infinity, I mean, whatever. But let's just say it's going off to plus or minus infinity. You can still analyze the endpoints by, you take, this is f of x, you take the limit as x approaches infinity of f of x, and the limit as x approaches minus infinity of f of x. That's how you can analyze the endpoints, right? You could treat the infinities as endpoints. And that's what they're talking about with horizontal asymptotes here, because if you get a finite number, like 3 or 6 or whatever, L1, L2, that's going to be a horizontal asymptote, right? It's going to approach a horizontal line. Y is equal to, it'll do something like this. That's what that example I gave where the function was approaching the speed of light was approaching a constant number as x went to infinity. So again, you're not drawing the curve yet, but you're just listing all this stuff. You're listing the limits as x goes to plus or minus infinity, or as x approaches the endpoints. But even if you get the limit as x approaches plus or minus infinity of f of x is equal to, let's say, negative infinity, well, that's still good information for curve sketching. So, because you know that if x is approaching infinity, the function is approaching minus infinity, you're going to have something like this, right? You're going to negative infinity as you get further out from the origin. But then from an analysis standpoint, that's really valuable to see how, okay, well, as this variable goes to infinity, the function is doing this. It's ballooning as well. Okay, now it mentions vertical asymptotes here as well. And so remember, a vertical asymptote is, they call it a vertical asymptote because you're taking the limit as x approaches a finite x value. So like as x approaches 3, well, x is equal to 3 is a vertical line. And so if you're approaching a finite x value from either side and that limit is going to infinity, either plus or negative infinity, that's a vertical asymptote. And so you're gonna find it, see if you have any vertical asymptotes, and then you're gonna kind of draw the vertical line there to get ready for curve sketching. Okay, so now what's the process for this though? Because you don't really, like we've talked about, you can think about, you don't know what the function looks like. That's kind of why you're analyzing it. Well, so if let's come here for a second. This intervals of, you're going to find the intervals of increase or decrease, local max and min values, concavity and points of inflection. The idea is, and I touched on this in the previous video and the previous few videos. So what we talked about is that you can, if you want to find, okay, let's say you want to find the intervals of the increasing or decreasing intervals and the intervals of concavity. That's something else you're going to want to do. Well, what's the process for that? What you do is you find the critical points. Okay, for E here, you find the critical points. You take the first derivative and find where the first derivative doesn't exist or it's equal to 0. And then what we talked about, what I mentioned, I summarized this in the last video, is that the function, the first derivative cannot change signs unless it crosses over a critical point. There's no other way. It has to change signs at a critical point. And so that's how you're going to analyze. You're going to go to each of the regions in between critical points and plug in a value in that region to see if the function is positive or the first derivative is positive or negative. All right. And when it comes to analyzing concavity, it's the exact same process, but you can think about but you do this with what I called, this is not a math term, but like second critical points. It's critical points with respect to the second derivative. So where does the second derivative not exist, and where does the second derivative equal to 0? The concavity won't be able to, the second derivative can't change signs unless it passes over a second critical point. Okay, but the thing is though, so once you've got these first and second critical points, so yeah, you can find what the intervals of increase or decrease are and the intervals of concavity are. But from there, what you would do is, so let's say you skipped the, at the asymptote section, you analyze the endpoint behavior, the limits going to plus or minus infinity or to the endpoints, and then you skipped over the rest and came here first to E and G. Then once you've got these critical points, these first and second critical points, what you would do is you would take the limit as x approaches each of those first and second critical points from the left and the right. And if any of those approach plus or minus infinity, it's a vertical asymptote. But even if it doesn't approach infinity, it's still useful information. You still want that information. And that's how you would, because the idea is you don't know what the function looks like. And there's no, but you can't, there's no way to have, you're not going to have a vertical asymptote unless it's at a critical point. I think it would just be if that's at the first derivative critical point, but you could still do the same process. It's still good practice to do the same process with the second critical points as well. Okay? So that's how you would get your vertical asymptotes. If the limit as x approaches a first or second critical point from the left or the right goes to plus or minus infinity, it's a vertical asymptote. Okay? And just to point this out, as far as the main functions that we've analyzed in algebra and trigonometry, the only time you come across a vertical asymptote is any situation where you're dividing by 0. So g of x over h of x. But as I mentioned, when in the next section, we're going to talk about L'Hopital's rule. Just because you're dividing by 0, if the x values that makes this h of x 0 are the same x values that make g of x 0, then that's not necessarily a vertical asymptote. But in general, for the most part, if it's in a case where you're dividing by 0 and you've got something non-zero in the numerator, that's a vertical asymptote. That's the case. But then there's also every single trig function except for sine and cosine has vertical asymptotes as well. So you remember tangent is like, and it's periodic. Okay. All right. Now, then there's also slant asymptotes, and we'll come back to this at the end of. And let's go through all of this first. All right. So you determine your intervals of increase or decrease in the intervals of concavity. But then you also want to find any local maxes and mins and inflection points. And I reviewed this the meaning behind this and this process in the previous video, but you're only going to have these are only possible at critical points. Local maxes and mins are only going to be at the first derivative critical points. Inflection points will only be at the second critical points. And just note that you can have an inflection point and it not be a critical point with respect to the first derivative. Just note that. All right, but so you would take all of your critical points and see, do I have a local max and min? You would apply the first derivative test to it, and even the second derivative test if it applies. And just because you don't have a local max or min, you still want to note that it's not a local max or min for the sake of analysis and curve sketching. So, if you have something like this, well, this is not a local max or min, but it's a critical point. Well, still, you note that it's not a local max or min, but it's still, you just note what it is. And same idea, if you have an inflection point where, or if you have a point where the second derivative equals 0, but it's still not an inflection point because it doesn't change, the concavity doesn't change sign, it's still a point of interest, right? Okay, so again, I reviewed in the previous video all the ideas behind determining local maxes and mins and inflection points. So you would note all of these interesting points, these critical points that either end up being a local max or a min or a point of inflection, or if they're not, you still note what's going on at that point. Every critical point, every first and second critical point, for the sake of analysis and curve sketching, you kind of want to note what's going on at that point. Even if it's not a local max or a min or a point of inflection or a vertical asymptote, well, what's going on there? What is it? Okay, so we just need to talk about slant asymptotes. That's the last thing the book mentions before you sketch the curve. But before we go to the slant asymptotes, I want to note that I mentioned that for this case, you could analyze the limit as x approaches the endpoints from the right here, from the left here, but you could also analyze the first or second derivative as x approaches these values. So that concept of taking limits as x approaches any point with respect to the first or second derivative, if you really wanted to get into detailed analysis, just that option is always there. So like I mentioned, when you find all the first and second critical points, that for the asymptotes, you take the limits as the x approaches those critical points from the left and the right, and see what happens. You could take the limit as x approaches all of those critical points from the left or the right of the first derivative, of the second derivative. So like if you had, a function that does something like this. Well, okay, this is a critical point. If you're curve sketching, well, wouldn't it be nice to know what the slope here is as x approaches this 0 from the left and the right of the limit as x approaches 0 from the left and the right of f prime of x? Then you could get an idea of what's the slope as you're coming in here, and that would be interesting from an analysis standpoint. What's the curvature as you're coming in here? You don't have to do this. I'm just trying, again, this is just, it's all in your toolbox for analyzing a function. If we did we're not going to do that. We're not going to do that when we do curve sketching. We're just going to do like curve sketching example problems. We're just going to do what the book lays out here. We're not going to take these limits as the x approaches this from the left of the first derivative. I'm just saying in a real situation, or if like your teacher said, okay, you've got a week I'm going to give you one curve to sketch, and you've got a week, and this is going to be for your entire grade, and it's got to be the best curve sketch ever. Well, that's what you would do. You'd be taking limits of first and second derivatives and the function all over the place to get the slope exactly right. You know what I mean? So but even from just an analysis standpoint, if this has a physical meaning to it with respect to like engineering or physics or economics, what's the slope of the curve as you come in here? Could be interesting. But you could do that. You could take those kind of limits anywhere you want. It doesn't have to be just at first and second critical points. You could do whatever you want. Whatever you think it's interesting, you could do that. You could take a limit as x approaches a number in general, as x approaches a number from the left or the right, of f of x, f prime of x, f double prime of x, whatever you want. So just note that. Okay, now let's look at slant asymptotes. Some curves have asymptotes that are oblique. That is neither horizontal nor vertical. And so what they're talking about here is this is a parallel to a horizontal asymptote. So what I mean is this is as x approaches plus or minus infinity. So the horizontal asymptote, it's as x approaches plus or minus infinity, the function is approaching a finite value. But a slant asymptote, as x approaches plus or minus infinity, the function is approaching a line that's not a horizontal line, but a slanted line. Not a vertical line. It's not a vertical asymptote. It's a slanted line. Okay, and so to understand this, let's take a look at the example they give so you can understand this. This is just one example. But if you've got here they give a rational function, and the numerator, the order of the numerator is greater than the order of the denominator. And so what they first do is they do polynomial long division. All right. And so they can rewrite the function like this from polynomial long division. And so what they then do is they bring the x to this side. So you have f of x minus x is equal to this. Okay. And then now they take this limit here as x approaches infinity, and this goes to 0. And we did a lot of limits like this. It's a rational function, rational expression with the order of the numerator is less than the order of the denominator. This is always going to go to 0 as x approaches infinity. Okay, and so what does that mean? What they're saying that is that, so if you start here, okay, let's take the, so okay, you got let's take the limit of both sides of this equation right here. So you've got the limit, let me put this to the side here. Okay, you've got the limit as x approaches infinity of f of x minus x is equal to the limit as x approaches infinity of, so okay, so that's valid, right? We took the original function, we rewrote it like this, and then we just subtracted x from both sides. So we got here, okay? And now we just took the limit as x approaches infinity of both sides. So we haven't changed the equation. And what they're saying is this limit goes to 0. So what you're left with is the limit as x approaches infinity of f of x minus x is equal to 0. And this is the key idea. The line y is equal to x. Okay, you can draw the line y is equal to x. As x approaches infinity, the difference between the original function and the line y is equal to x is approaching 0. So that's how it's a slant asymptote. You see, it's the function is approaching this line. That's what they're talking about here. It doesn't have to be just y is equal to x. You could have any line, mx plus b. If you can write it this way, where the original function minus, and any line, mx plus b, is equal to 0, then that's going to be a slant asymptote going to plus or minus infinity. And, just to point this out, you could technically do this with any kind of function. So like if this was the limit as x approaches infinity of f of x minus x squared is equal to 0, then as x goes to infinity, you'd be approaching this parabola. But they don't go that far. I think what they want to do is, you have a horizontal asymptote, that's a horizontal line that's being approached. You have a vertical asymptote, that's a vertical line that's being approached. And then there's also approaching a slant line. That's the idea they're going for. And what's interesting is, to me, is if for a situation like this, if you took the limit as x approaches infinity of x prime of x, then it's going to be the slope of the line, right? So that's another thing you can do. You could take the limits as x approaches plus or minus infinity of the f prime or f double prime. So when you're drawing, even if you don't have a slant asymptote, when you're drawing your function, and so that the limit, let's say the limit as x approaches infinity is going to infinity, let's say, But then you also, how are you going to draw the shape out here? Are you going to draw a line? Are you going to draw what is the slope? What is the slope doing as x approaches infinity? So it's another thing you can analyze. I mean, you can imagine for like a slant asymptote, as x approaches infinity, f prime of x is going to approach 0, right? So it's all kind of ways you can analyze the graph. Okay, and then from there, you just sketch the curve. You have all this information, and you can sketch the curve or just analyze the function. And the rest of the section just gives different examples of curve sketching. But instead of going through these, I mean, we're gonna in the upcoming videos, we're gonna do a bunch of different examples, go through it slowly of doing all of this, sketching the curve, just doing all these steps. So we're going to go through a bunch of examples in the upcoming videos, and I'll make sure that, that we go through all the different types of examples. So like they show periodic functions, they do all kinds of all the different potential scenarios. And so that's what we're going to do in the upcoming videos. Okay, let's work some example problems.